So hi, I'm Alex Remedios, and I'm an AI-focused site reliability engineer. And I'm the founder of TreeBearTech, an MLOps company based in London, in the UK. And in this talk, I'm going to be telling you about the COVID-19 early warning system project, one of the most meaningful projects that I've personally worked on. And I'll also touch on how you can operationalize Bayesian models at scale, how you can use Ray even in critical infrastructure projects, and hopefully I can give you some takeaways for how you can build AI infrastructure using Ray and calibrate. So I want to just set the scene and tell you a bit about the situation when this project started, when COVID-19 was starting to arrive in the UK. There was a period of extreme uncertainty in March of 2020 when COVID was reaching the UK, and around this time there was the first confirmed COVID death. There was not a lot of clarity in terms of how the National Health Service hospitals would be able to deal with the growing demand for beds. And the potential human cost of the virus was subject to quite a bit of speculation. So, like many countries around this time, within weeks of the first COVID death, there was a stay-at-home order issued by the Prime Minister. And this began a period of over a year of lockdowns, and it was an extreme measure taken to protect the NHS from reaching capacity and having people unable to access healthcare. So apart from trying to minimize the demand for healthcare in the UK at this time, like the USA as well, the UK created additional hospital beds, trying to create more capacity to accommodate patients. But there was another initiative as well on the operational side, and that was to figure out how do we better allocate existing resources. And pandemics have been studied a lot throughout recent history, and at this time, the data sets were becoming better integrated, and there was the understanding that you could actually model waves of infection throughout the UK at different locations and generate short-term forecasts to understand how many resources a hospital may need in the near future. So this led to the early warning system project, and this was executed by a customer, Faculty, a leading AI company in the UK. They specialize in decision intelligence, and they created Bayesian models for the NHS that would give each hospital a unique forecast that would help them understand their demands for the next few weeks. And just a little bit about this system from a technical perspective. There were different types of stakeholders, and the main one obviously was the UK public. So these would be patients that may catch COVID. They may then need to be admitted to hospital, and once in hospital, they may additionally need intensive care in an intensive care bed. But then the system would also have end users. These would be the NHS staff at the operational level. They would be figuring out, either for an individual hospital trust, how do we have enough resources, enough beds, enough ventilators to cover us for the next few weeks, and maybe at a regional level as well, how do we allocate resources across a number of hospitals and potentially move patients between hospitals to balance demand. And then on the operational side of the actual tool itself, there were developers. These were data scientists and machine learning engineers. They would be creating new features for the models, doing constant QA, making sure that whenever they were sending out forecasts to hospitals, that they'd been checked for any issues. And of course, there were project managers throughout just checking that the tool as a whole was serving stakeholders in the NHS. So this is what the early warning system looked like to an end user. So if you were an operations manager in a hospital, you would see a curve of recent demand relating to admissions to the hospital, and then the early warning system models would create a additional set of lines showing you the possible needs over the next few weeks. These were Bayesian models, meaning that they would have uncertainty factored in, and as a result, they could give you a range of possible scenarios in the near future. So let's just get into a bit more technical detail about what the underlying technology here was doing. There were two features that were user-facing. So NHS staff could access forecasts, which would tell them how many patients would be admitted to hospital potentially in the next few weeks, as well as explanations. And these were based on counterfactuals that were run by the system. And that would tell NHS staff what caused the model to predict an increase in admissions and what caused the model to predict a decrease. So this was necessary for using the actual forecast in the context of the data. And then on the internal side of the platform, there would be constant batch jobs that would be calibrating recent forecasts against ground truth data. And there would be constant retraining processes, hyperparameter optimization that the data scientists would be running. So different types of workloads all operating roughly on the same data, but for different means. Okay, now let's have a think about what the system was like for data scientists, machine learning engineers. We obviously want to give people the ability to write scalable Python functions in some way. And as an example, if we could give them a framework where they can write a forecasting job where they have a Python function to pull data and then run batch inference, then ideally they can annotate the function and run this in a cloud environment. And this is exactly how it worked. So initially, the orchestrator involved was called Dagster. And Dagster is similar to another tool that people might be familiar with called Airflow. And this would let people run these graphs of operations. So Dagster for directed acyclic graph. So they would write their function, and then they would have a graph that they could deploy onto a Kubernetes cluster. And you can see here that in this example, there's a few serial loading jobs at the start, and then there's a fan-out where you can train and run inference on multiple models, and then there's a combination part at the end, and this is where it would upload any predictions made to a forecasting dashboard. And this problem, because we were fitting models and running predictions for lots of different NHS trusts throughout the UK, it was inherently quite amenable to parallelizing. So you could load data and then run a model for each different location, generating a single data set at the end. Then on the architectural side, to give you a really top-down view of how the system worked, initially the NHS staff were the end users here, and they would check a dashboard which would be populated every day. This was built around a common data warehousing analytics tool called Palantir Foundry, and then faculty's early warning system code would be running on a separate Kubernetes cluster on AWS. And every Dagster task, for example, for generating a forecast for a single region would run in a single pod, making it scalable across the cloud. And this is generally how things were operating. But there was a really serious problem with this approach, and that is that if you provided a very large DAG of operations, maybe you wanted to run a grid search, and you entered a very large search space, it could create a huge number of pods in a short amount of time. And it turns out when you create too many pods in a Kubernetes cluster, the entire cluster can fail. So there's a bunch of things that go wrong, but maybe someone wants to suggest what the first thing is to fail when you create too many pods in a Kubernetes cluster? Feel free to shout out. Not enough nodes. Well, there was auto-scaling, so it would create more nodes. Then what happens next? Okay, yeah, control plane, yeah. So you might think, oh, the DNS can get quite overwhelmed at some point, but yet eventually you create more nodes, and then the nodes will have the pods assigned, the nodes also have daemon set pods, and then eventually the control plane fails, and in this case, the control plane would run out of storage because every single pod would have a certain storage footprint on the control plane, and when the control plane runs out of storage, it becomes unavailable, and I'll go into that more in a second. But it turns out that particularly large grid search operations for hyperparameter optimization would occasionally create about 10,000 Kubernetes jobs in a 10-minute period, and this was causing the entire platform underpinning the system to fail. I probably don't need to explain in really granular detail why this is bad, but this would affect the end users. They wouldn't be able to see forecasts the next morning in the product, and this would reduce the chance that they'll actually come back and check this and use this as a part of their operational processes. But on the developer side, people would lose everything from their Jupyter servers to dev jobs that were running and hyperparameter optimization. And also then the machine learning engineers and data scientists would require a platform engineering team to come in and fix this. And the next time they would run a smaller, less thorough batch job, and we want people to be creating larger, more ambitious systems, not the smaller ones. So there were a lot of reasons why you wanted to fix this. And when we did some analysis, we found that there's a load of reasons why an outage occurs. You can think about, I felt like the most high impact reason is that data scientists could only scale their Python functions using a single mechanism, which was a node in a Dagster graph. And each node in Dagster graph would create a single pod, and that was the only way they could scale things up. But also you could think that using the Kubernetes control plane too much. When the Kubernetes control plane fails, they were self-hosting it using kops, and it would not be self-healing, which is a problem. But also, like, when you have data scientists using a platform, you want them to be able to run something as large as possible, even until it fails, and not affect other people's work. And so maybe it's not bad that it fails, maybe it's just bad that when it failed, it took the rest of the system down with it. So like guardrails. And then finally, there was very little indication that the platform was going to fail, and an alarm would be sent, but it would be too late by that point. So the observability was quite poor. I'm going to tell you about the highest impact fix that we put in throughout this time, and that was finding a better way of scaling Python functions, and this is what led us to Ray. And there was a period of reevaluating what do we actually need from this system, because the funny thing is that it wasn't a particularly large-scale use case. There was a large amount of data involved, and the batch system would require using in the order of thousands of cores overnight, but there were a lot of different tasks going on here, and it turns out that most of them did not require distributed computing. So forecasts and explanations are the user-facing features here, and they had to run in 8 hours. But then there were calibration tasks and grid searching, and there were a bunch of different needs for each of these. For example, grid searching was very amenable to parallelization. You could run it very quickly if you wanted to run 5,000 tasks in parallel. It would require about 10 terabytes of memory, 100 nodes, and 500 pods. With the way that we're running with Dagster, 5,000 parallel tasks meant 5,000 pods, but in reality, if you just need 10 terabytes of memory, you actually don't need, you can get that amount of memory in just 500 pods. But forecasts and calibration, they didn't even need to be distributed. So if you need 50 CPUs and 100 gigabytes of memory, you can get that in a single AWS instance. But the reason why we were in distributed computing territory was because the explanations needed to run in 8 hours, and that did require maxing out the parallelism and getting 1,000 cores on it. So the first thing we thought about doing was making sure that every function that runs doesn't create a new pod in Kubernetes. And that meant that we experimented with switching Dagster out of running one pod per task to running a pod for an entire task graph. And this immediately simplified things, but it also led to the loss of ability to run the explanation task, which required 1,000 cores. And for reference, in AWS, the largest you can really get in most regions with a single pod is about 96 CPUs and around a terabyte of memory. So we needed about 10 times more than that. But most of the workloads could run on here really well. And so that was kind of a breakthrough saying, why don't we try running Dagster this way? And then let's find something different for running the distributed part. So we identified that for the explanations, we can start it off in a single virtual machine. And then when it gets to the bit that needs to run across 1,000 cores, we're going to have a separate array cluster. And the sub-process, so when you switch Dagster into this single machine mode, each operation will run as a sub-process rather than a Kubernetes pod. And the sub-process can call out to an array cluster and create a ton of tasks against the array cluster. And then you can have a small number of extremely large workers behind the scenes there hosting these tasks. And going back to the user experience here, for the machine learning engineers, they would still be able to write Python functions, but instead of annotating it with a Dagster annotation, they'd annotate it with array annotation. And it was really important that we kept that kind of productivity, even though we were quite seriously re-architecting the processes behind the scenes. So assuming that most people here haven't used calibrate before, I'll quickly run through how it would work at runtime. So you'd have a run container in Dagster. It would submit tasks to a array cluster head node. And then you would have an autoscaler that would understand that this small array head node isn't here to execute work. It's here kind of just to register the work. So it's a control plane within the Kubernetes control plane that's isolated just for this task. And then the autoscaler kicks in and asks the Kubernetes API for array workers, and then the array workers will pick up work from the head node and execute it. And how do we actually implement this infrastructure? So there'd be a infrastructure as code, a Helm file-based solution in the Python repo that had all the modeling code. And you could build a Docker image and pass it to a array cluster custom resource implemented by Kubernetes. And that custom resource would create pods for your array cluster. And then once you have a pod for your array cluster, you need some auto-scaling mechanism under the hood to provide a node for it. And we found a really good fit with the Carpenter project, which lets you also use a Kubernetes custom resource operator pattern for saying, these are the types of instances we want to be running our work on. And rather than creating auto-scaling groups for every type of instance, we could just pass values in here and say, we want R5, 8, or 12, or 24 X-large instances, and they could host tons of tasks in parallel, which gave us a better ratio of parallel tasks to underlying pods in the control plane for Kubernetes. So looking at this new platform that we put together as a whole, you could think about it as there being app environments. And when a data scientist or machine learning engineer builds their Python code, they could then deploy it as an app environment, and that would have its own Helm chart. And they would have one instance of their user code image running as a Dagster user code service, and they'd have another one running as a array head node in a scaled down manner with an autoscaler ready to scale it up. And on the right, you can see that when it goes into production and starts to be invoked, the Dagster job would start running their user code, and that would then call the Ray head node, and Ray workers would be created also in that same user code context. And then underlying this platform, we had a suite of Kubernetes-based operators and tools. Just to list out a couple, we had a new observability stack, which was really valuable for letting people know if something was using up too much memory. And then the Ray clusters and autoscaling was implemented by the calibrate and Carpenter autoscalers. And I mentioned guardrails a little bit earlier. We had a system called Gatekeeper, and that would ensure that when one of the app environments was making calls to the Kubernetes API, it would have to have node selectors and tolerations and resource requests that kept users in a state that they could max out their own allocation but not harm each other's work. And what we were really going for here was high availability. So there were about two really big outages in the 6 months up to this re-architecture. And in 12 months following the switch towards using Ray for parallelism, there have been no outages. But apart from that, the capacity of the overall system has grown exponentially. With the Dagster-based parallelism, it was possible to get about 1,000, sometimes 10,000 cores, but you were always straining the cluster quite a bit. With the Ray and the calibrate architecture, the main limitation really is the cost and the amount of money you want to spend on hosts. The scaling bottleneck's completely been removed. And I think one of the best things that we take forward out of this is that the productivity of the team was increased by switching most of the workloads away from being distributed and towards a single host in a multi-processing environment. This is great because it runs the code in the same way it would run on their laptop, and it's easier to monitor a single host rather than a cluster of machines. So these are a few takeaways that I'd like to leave you with so that when you're building systems like this, you can hopefully take our experiences and move forward with them. It's funny at Ray Summit saying avoid distributed computing, but if you can, run everything you possibly can in a single machine, and then once you can't get a larger machine or you're spending too much money on that machine, it's great to just start taking on the complexity of distributed computing. When you do that, though, invest in observability, because you will lose a single thread of logs and metrics, and suddenly everything will get a bit harder to manage. And this overall method of giving people Python APIs that they can annotate and then scale out is really powerful. Just help people understand the semantics and give them guardrails for the underlying APIs that they're using. And when you allow data scientists to create Python applications that do scale out like this, try and decouple the structure of the application from the infrastructure load. So the one Python invocation for one pod was a problem, and that's something you should avoid. And finally, I can really highly recommend combining calibrate and Carpenter if you are on AWS. It's been a combination that gives people a ton of agency to essentially be bottlenecked only by the amount of money they want to spend on cloud instances. Like technically speaking, it was really robust. So really quick reflection. This was a very meaningful piece of work for me, and obviously I want to talk about it in context of the people involved. So throughout COVID, just in England where the project ran, there were 1 million hospital admissions with COVID. And really sadly, almost 200,000 people in England had COVID-19 on their death certificate. So this was an extremely challenging situation and an impactful project. But you've got to look at the numbers and understand that AI in healthcare is in its early days, and I'm really optimistic that continuing to have initiatives like these is going to save and improve lives long into the future. So thanks so much for listening. And just a few acknowledgements, like big shout out to the faculty early warning system team and the staff in the NHS that made this project happen, and also to the open source community. I mentioned calibrate and Dagster quite a bit here, but there are so many projects that have that have helped make this early warning system come together. So thank you, everyone that is involved in the open source community. And with that, and by the way, if you want to read more about this or listen to the podcast that I did with Ben ahead of this talk, go to treebid.io. And if you're building anything and you want to chat about it, reach out and connect with us on the socials. So yeah, there's just a few minutes left for questions. Anything that anyone's curious about going over, there's a bit more time, so feel free to ask some questions. Hey.
How accurate was the system, and also how were the models able to take into account like potential variants in the future that had different factors like spreadability and hospitalization rate, and was it able to like foresee those kinds of spikes in hospitalization?
Yeah, so for how accurate the system was, so I have to admit that at the infrastructure level, I was quite insulated from the day-to-day operation of the models. But I would recommend checking out the faculty's website to understand that in more detail. It's faculty.ai. They've got a case study on it. And for different variants, we were quite focused on the operation of hospitals, and so we were living much more in the world of admissions and intensive care beds. But there were notable spikes in COVID rates as new variants occurred. And so this system under the hood used the idea of waves that would be configured. So there was like the first main wave of COVID, and then there were a series of waves. Like, for example, there was the Omicron variant in December of 2021, I think. So they thought about it in waves more than variants. And in terms of like finding more features and use cases, I think they experimented quite a bit with different features for the models and different data sources. But overall, they kept it quite simple. Hey.
Elaborate how Gatekeeper works? You mentioned it. Just curious.
Yeah, Gatekeeper is really effective at creating like platforms based on Kubernetes. The way it works is that if you've got someone that you want to give them Kubernetes API access, for example, using Kubernetes or Dagster, you might want to ensure that their resources are capped at, let's say, 64 gigabytes per pod. And the way that we found it most effective is using the Kubernetes admission control and or webhook system. So when you install Gatekeeper, it will create a Kubernetes webhook, and you can configure it to say, every time a pod gets created, reject the request if, for example, the resource requests are too high. And you can also do more useful things, such as if there's no resource requests on it, set by default like 8 gigabytes. And because most data scientists, they don't think too much about like Kubernetes API level stuff, and they shouldn't have to. So Gatekeeper lets you fill a lot of those sensible defaults and give people guardrails. Any other questions? Anyone? Yeah.
What was the use case for ML flow?
Yeah. Overall, there was a constant process of pulling in data every day and retraining the models, because this was a time series forecasting problem. Every day, basically, your models would be out of date. And so they would, there were two different ways of registering data artifacts and models. One was with Dagster, which it doesn't just orchestrate workflows, it also lets you like track data versions. But MLflow was a slightly more dedicated one. So there were a couple of teams. One of them used Dagster for tracking artifacts, but the other one used MLflow. And personally, I found MLflow to be slightly better for when you needed to port data around afterwards. Did that answer your question?
Yeah.
Thank you.